I'm hoping that first one didn't give us too much of a problem. Why does the 3 not really bother me?
It's just an A.
It's just a constant, right? So I really think about it like 3 times this. And how would I do 1 over 1 minus x to the 4th?
You just replace x with x to the
Yeah,
fourth.
just replace x with x to the 4th. And then just bring the 3 through. Right, so it'd be 3 plus 3x4 plus 3x8. And then how would that look like in summation notation?
3x to the
Yeah.
n.
Cool. Again, you just plug an x to the 4th into the summation part itself also. It's almost too easy, really. Everybody expects it to be disgusting, but it's really not that bad. Let me ask you this real quick. I know that x itself is a variable in the sense that I can change it, but the minute I change x to 3 or 4 or 1/2 or whatever, I have a series representation. According to the series, what is the variable? According to the series itself, what is the variable? N. So according to the series, what's x?
Constant.
Constant. For any given value of x, all this is some number, right? So this one works the same way as that one. Same exact way. I can look at this as x times 1 over 1 minus x. And 1 over 1 minus x is the first thing we're working with. How you guys doing? Now that's where you got to be real careful, because I still have people that somehow take x's out of integrals, which is a big no-no because the integrals variable is x. Here, I can't take anything out of a summation that deals with n, because that's the variable that's involved in that summation, right? I can't take something out that's not a constant. But according to the series itself, x is a variable. I mean, it's a constant, right? It's a constant. So I can bring it in. So here's x sum, and just like over there. So then I get sum of n equals n 0 to infinity x to the n plus 1. Bring the x in, right? How are we doing? Is that all right? I mean, that's really shouldn't be a huge deal. We've done stuff like this before. The thing that really gets people, I think, is that according to this series, n is the variable. N is the thing I can't take out. If there's an n here, I couldn't just take it out. That would be crazy. But for any x I pick for this function, the series still sees it as a constant. It's just whatever number I happen to pick at that moment. So it can still go in and out. X can go in and out of here, no problem, because this is based on n. So this sees x as a constant. Okay. Hopefully you guys see that. I think that's the point that really mixes people up. What about this guy?
Not like a
Take the derivative.
Yeah, so one way to approach this, and actually I like this approach a little better than what the book does. Same math though. This guy's derivative is
1 over 1 minus x.
what's that? Say again?
1 over 1 minus x.
Almost.
-4.
Cool. Right, because it'll be 1 over 1 over this times the derivative of this, so that -1 pops out, right? So the derivative is really just this. The derivative of the function that I want. Everybody see where I got that from, of course, right? That's just negative that guy that we've been working with this whole time. Blah, 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 which I can write in summation as just negative on the outside, like that. Now, how do I get from this back to what I want then? Of course, the huge hint that I gave you.
Take the antiderivative.
Take the integral. Take the antiderivative. I like even better, right? So this would become
X.
negative x.
Negative x squared over 2. Negative x cubed over 3.
Dot, dot, dot. And here's why I love, it's so much easier just to attack the summation itself directly instead of doing the parts. You can always bring the parts out if you can get the sum written down. What's the integral of x to the n?
Negative.
X to the n minus 1.
Cool, right? Now, when you do an integral of a series, though, what should the first thing be? And there's a negative on the outside, so don't worry about that. The first thing should be x, right? And if I make n equal to 0, I get my x, don't I? So you should just make sure that your whatever you're doing with your series actually agrees with what you should get. How are you doing? Because that index sometimes will change. They make a big deal out of when you take derivatives, the index changes just because that first term might become 0 if it's already a constant. So for example, what's the derivative of this? 0, right? So that's why, I don't know if you guys noticed earlier, I made this n equal 1 there, because n equals 0 would just be 0 then. So let me do that specifically, because this happens every now and again. And I want to show you how you can put it either way. What's the derivative of this? It would be 0 plus 1 plus 2x plus dot dot dot. And we said it was 3x squared. So we said it was sum of n x to the n minus 1, because that just taking the derivative of that. But if n equals 0, don't I just get 0? So what you'll see the book do, and this is why you can leave it n equals 0. Does it make it wrong? No. But you're sort of picking up a 0 term, which is kind of conventionally, we don't want to do that. So you'll see the book always change the index to 1 there. Because who cares about 0? Does that contribute anything? No. So they want to start at the first non-zero term. So they change the index to 1. Oh, let's see if I can find one real quick. Oh, here. No, they didn't do it. Screwed up. All right. They give you, I mean, the examples in here are really good. When you get something a little freaky like, oh, where's that one? Oh, this isn't even that freaky. But if I had like 1 over x plus 2. For right now, our whole purpose is to try to make it look like this. So how could I make it look like that? I want to make it look like this, right? So I could first turn it around and make 2 minus negative x. I mean, that's fine, right? But what's there that shouldn't be there? 2. So it's exactly like this 3. What did we do with that 3? We just got it out of the way. All right? So we could see what's really there. And then at the end, we just put a 3 across everybody. Who cares? The 3 constant comes out, goes in. Awesome. Same thing here, except what do I take out now? 1/2, and then what are you left with?
1 minus 1/2.
Negative x over 2, right? If you take a 2 out of the bottom, you would take a 2 out of the bottom. Not just the piece of the bottom. The bottom. Cool. That's the type of thing that happens all the time in calculus. All the time in calculus, and I always get people kind of mess it up a little bit. But just remember, when you take something out, you divide it out. So what's x divided by 2? X divided by 2. Cool. Because that's what I took out. And what would that be now? It would be 1/2. What do I replace x with now? Negative x over 2, right? So it would be 1/2 times 1 minus x over 2 plus x squared over 4 minus x cubed over 8, blah, blah, blah. And if you look at it from this standpoint, I replace x with negative x over 2, right? That should be the same thing. And sure enough, we see that, bring that 2 in, take the negative 1 out, bring the 2 in. Well, the 2 really is kind of weird, but oh, too bad for us. Let's see if you guys are cool with this. Is that all right? I brought an extra 2 in there. Be real careful. This is where it's real easy to go, okay, that's 4, yay. But you have n 2s, so now you have n plus 1 2s in there. How's that? Is that all right? All right. I love you guys' reactions based on the knowledge. That is most interesting. All right. And the reason I do this, I love, you do this by this, you do this by this, and then you just take a second to make sure that you actually get those. Right? So if you did plug a 0 in, you get 1/2, you get 1/2. Sweet. And you try to plug a 1 in, make sure you get the next thing so that everything agrees, and then you move on. Okay. Now, so 11.9, obviously 11.9 really focuses on 1 over 1 minus x. You're going to eventually, you might already be there, get really sick of that function. So thank God we say, okay, we can do all this crap. We can do so much crap if I know the representation of a function as a power series. Right? We can do all this stuff. And real quick, let me show you a concrete example with this before I get too far into more abstract stuff. So what if I had f of 1/3? Then this would be 1 over 1 minus 1/3, right? Which is 3/2. Cool? But let's say how far, let's say I go out, so it'd be 1 plus 1/3 plus 1/3 squared plus 1/3 cubed. If I only go out that far, how close do I get to the actual answer? So it should be 1.5. What do I get here? I get, let's see, 1/27 plus 3/27 plus 9/27 plus 27/27, I think, right? Kind of wrote it backwards. Is that cool? Bam, 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 bam. 36, 39, 40 27s. And what's 40 divided by 27? 39 over 26 would be 3/2 exactly. So 40 over 27 should be pretty damn close.
1.48.
Sweet. So this is what I was saying earlier. I want you to see a concrete example. If you're okay with being that far off, then you only have to go out to this term, right? And you could go a few more terms out just to be careful, and then start doing derivatives and integrals and stuff, and it should be good out to a decent number of decimal places then. So now you're working with a polynomial instead of this uglier function. And again, what's the thing I got to be careful about? When I go to start plugging stuff into my function, what do I have to know before I can plug just some number? If I plugged f of 2, who can tell me why that should freak out? Is there a reason that should freak out? When does this thing converge? X has got to be between -1 and 1, right? That's my domain then of this function. Those are the things that I'm allowed to plug in without it becoming some kind of infinity or some weird oscillating thing, right? You guys with me? So the ideas of domain and range are still applicable. The interval of convergence is now kind of my domain for these functions, these power series functions. If I use something outside that interval, it's either going to go to infinity or it's going to oscillate, which means my function is going to be undefined there in some way, right? So it's the same thing as old algebra stuff. There's certain values of x that lead you to good answers. There's some values of x that make it freak out. Right? Just like algebra. Well, it isn't. So